Right now, thanks you also. Thank you, kind sir. So that's what, 1.6. All right? Dividing by 5 is easy. You double it and then you move the decimal over 1. Bam. And how do I get the standard deviation then?
Take the square root.
Take the square root to kill that square, right? So what's the square root of 1.6? 1 point something.
1.26.
So here's the thing, you ready? Here's something. I talk fast normally, so when I slow down, that's a big key note. The slower I talk, the more important. Standard deviation, you must always round it to at least 3 decimal places. Right? And in fact, 3 non-zero, meaning if it come out to be 0.00000457, I would make it 0.0000458. Because those zeros don't mean shit. If you've taken any science classes, you kind of know what I mean with sig figs, but don't worry, we're not going to bring those in. Always round your standard deviation to at least, so what does it come out to be? 1.265. 265? So what does that mean? That means, and it's not perfect because we had to square and square root, which doesn't keep things perfect, but it's a lot better than this hard kink that an absolute value would do to me. It means that the approximate average distance away from the middle to all the data points is 1.265. So if you did this whole thing again, for this data, what should be different? Exactly how would the number be different? It should be bigger, because the spread of this data, like we said at the beginning, is more. So do it. Do everything we just did, but with this data instead. Did somebody say, Professor, what happened? Am I going crazy? Oh, bless you. You guys with me? Is this what you got so far? Right? You're going to first calculate, if you want to find an average distance, it makes sense you first calculate the distance, because then you can average it. You have to square to kill the negatives. I know a lot of you guys are going to make it just a little m because it makes sense for mean, but try to make it a little u with the extra leg. So what's this? What's the sum of this?
10.
10. So that is 10. So wherever you see it, you're going to put a 10 in place of the whole damn thing. You're not going to plug stuff here and here. Which, because that wouldn't make any sense. What is x? Several things. Do you see what I'm saying? So you can't plug something in for x, because x is all these at once. Oh shit. So in place of this, I put 10. What do I put down here? 5.
2 square root.
Good. 1.414. Kick ass. Did it do like we thought it would?
Yes.
It was supposed to be a little bigger than that. Not much bigger. It's not like crazy spread out, but it certainly is a little bit bigger than that. Beautiful. So it does what I wanted it to do. I've got a number that tells me the middle. And though the median is there too, but the mean is the number that takes into account all of the data points. So it's more generally useful for this kind of stuff. So the mean kind of won out, even though the median is sometimes better to use. So I got a number for the middle, and now I've got a way to calculate a number for the spread. If I told people those two things, they have a good feel for my data. It's just like me telling you, oh yeah, they give you average of a C, but this is the spread for that person, this is the spread for that person. There, you can make decisions now based on just that. Okay. Okay, so let me give you this. Let me show you this first. Here's, in case I give you a large set of data. Let me show you how to do all this in the calculator. And then I got a handout that's got sort of the calculator stuff on it. There's some extra stuff here, so let me not give it to you yet. So again, we're almost going to be using stat all the time, right? Stat seems to be a very important button. So we did this already. We put some in there, we sorted it. Well, this is a very small set of data. So put the data into L1. Now here's what's really cool. I don't think we've done this yet. Do you see how I have L2 highlighted? So if you're over there, just go over and then up. So L2 is highlighted. So L1 is my X's, right? What do I want L2 to be? Where are my X's? L1. So I want L2 to be L1 minus 3 in this case. It's not always 3. It's just because the mean here was 3. Right? So if I highlight L2, I can define what the whole list is. I want L2, see at the bottom how it says L2? I want L2 to be L1 minus 3. Bam. So you can imagine this is really useful if I give you like 27 data points. I just want to be able to do that and have it plop it all out for me, right? Yes, ma'am. Sure. And I'm supposed to be getting a bag O calculators at some point. Since I moved offices, I had to leave my bag of calculators for my old office mate. I'm supposed to get my own, so I'll bring them on the day of the test if you don't have a TI yet. So go up to L2, and again, this is all on your calculator Bible, on the website, that you can print out if you want to. Go up to L2, and then tell it you want the whole list 2 to be all the stuff in list 1 minus 3. So that is saying X minus the mean. That's what I want the second column to be, right? And of course it'll do it just, if you've ever used Excel, it's a little bit like that. You can define a whole range of values. In fact, if we had enough computer labs, we'd probably teach statistics on Excel. That'd be great, because Excel is a little more generally useful than TI calculator, right? But we don't have that much money, so too bad for us. And then what do you think I want L3 to be?
X minus 3 squared.
Even better.
L2 squared.
L2 squared. Bam! Where's my X minus mu in L2? So I just have to square L2. Now, real quick, here's the error you'll get. See where, am I in the right place? No. So if I try to tell it I want that to be L2 squared, it'll go, what the what? I'm trying to put an entire list in one spot. So the calculator's like, I can't do that shit. Whenever you have a go-to option that kicks ass, say go-to, and it'll say this is where the problem is. And I'm like, oh shit, I'm in the wrong place. Go up to L3. I want L3 to be L2 squared. Bam. All right. You don't have to, no.
Just trying to clear the
Yes, ma'am.
I'm trying to input the second, you put L1 minus 3, and my calculator just says quit. It just doesn't do it at all.
Oh.
Yeah.
Poor little thing. So do it again. You're in the wrong place. Sure. How are we doing? Everybody else all right? If you're playing along? Okay. So, and let me show you this last thing here. Hit second, quit, get out of there. And that's generally useful. If you hit something by accident, if you hit something like, where the hell am I? Hit second mode to quit, and it takes you back to the blank. It takes you back to the home screen. Right? What was I doing? Oh yes. If you go to second stat, go to list. Because what do I want to do with this? I want to add them, right? And again, everything I'm doing right now is in case I gave you, like 38 data points. I want to plus 2, plus 7. So if you go to math, so everybody, let me do this again. Hit second stat to go to list. And then I can do stuff to my lists. So I want to do math on my list. In fact, specifically, I want to sum. Which list? L3. I want to sum. So if I do number 5, sum L3, of course I'll get 10, right? Cool. Again, it's not. Hopefully you understand. I know we do this by hand, but if you had a long ass list today, that's useful. Yes.
When it comes to like the test, do you want us to do like that kind of stuff, like show the work on the
Yes.
paper?
So I'll tell you this once, but just to remind you, on the homework for the first test, you must show me. You're going to do a lot of it in the calculator, but then you have to copy it down. So like on the test, I want to see these columns, but you can do all the work in the calculator and just copy it down. The reason I do that is because subconsciously, at least, you're realizing what's going into this number instead of it just being, I pushed this button and it said this. That's bullshit. Right? After this first test, I am never going to make you do this again. Just once you go through that process, and then after the first test, we're going to use the standard deviation for a lot of other shit, so I just want to get it quick and do the rest of the problem. So then I'll in fact, let me show you how to get the standard deviation quick so you can check your work that you're going to do and show me. You ready? We already did this once. Remember that 1-bar stats? We did that, didn't we? So you hit stat, calc, 1-bar stats. Remind me, which list is my data actually in? List 1. So I want to do 1-bar stats on list 1, and that's what it defaults to. If I don't tell it anything, it's going to do list 1. So hit enter. And what up there looks familiar? Which number looks familiar? There's several of them. 3. That's the. It calls it X bar because it doesn't know if it's a population or what. It just calls it X bar to be the mean. So we know it's mu. But look what it does. Sigma is for a population. So remember, like X bar was the sample mean. Mu is the population mean. Sigma is this population standard deviation. S is the sample standard deviation. So samples are always going to have R letters. Not always. They're over here. Population is going to sometimes have Greek letters because it's a population. Sort of like the Super Bowl having Roman numerals, although this year I don't think they will. Who knows what it would be? It's the 50th one, right? So it would just be a big old L. Boom! L. It's not as impressive as XXXVII. Anyway, sorry. So for some reason, look, these are a little bit different. Right? The standard deviation, if it's a population, is this. That's what we got, isn't it? That's what we got. If it were a sample, this would be the standard deviation. Why? Why the hell is that true? So let's talk a little bit about that. Let's say you guys are a population. You're my population, right? There's an average. We'll just use age because it's easy to think about. There's an average age in here currently. That would be the mu of everybody. You guys with me? If I chose a row randomly to be my sample, is their average age going to be the same? I put money on it being different. I'm almost guaranteed that it's going to be different. You with me so far? It's either going to be lower or higher, right? So let's just say I happen to pick a row that has a lot of really young people in it. Hey, see, there you go. So their average, their X bar is going to be less than mu. Their sample mean is going to be less than the population mean, right? And all of their ages, they're all younger, so how far away from their own mean are they going to be? They're going to be closer to their own mean than they would be to the true mean. Let me say that again. Everything in my sample, everybody in my sample, their age is going to be closer to their mean than it would be to the real mean of everybody. Are you with me? So a sample standard deviation, if I didn't correct a little bit, is always going to be smaller than it's supposed to be. The distance away from the mean will be smaller than it should be because a sample is going to be closer to its own mean. I really want that to make a little bit of sense. That's why. So that's why the numbers are different. Now let's see what the formula would look like.
How does it figure out what's different? Doesn't it matter?
No. That's what's weird. I'm sorry. I knew you were going there.
Population?
Not at all. It's really nifty. And until we get to something called central limit theorem, which is, I can't remember which chapter is in this book. It's around the 7th chapter, somewhere in there. I can't really fully. It has to do with if I took every possible sample from here, and I didn't correct the sample standard deviation. I didn't change the number. And I averaged them all up. It wouldn't be the same as the standard deviation of everybody. But if I did make this correction for every possible sample of size, who cares? And then I averaged them, it would equal the standard deviation of the whole thing. You guys follow what I just said? I want to have a standard deviation per sample. If I did all possible samples of that size, they should kind of together become the real standard deviation, shouldn't they? Doesn't that feel like what should happen? If I took a sample, got a standard deviation, took another sample, got a standard deviation, took every possible sample of size 10 or whatever, I should be able to kind of like average them together to get the real standard deviation for everybody. That feels like that should happen. And it would happen if I use the adjusted formula. If I don't, it won't. So it's what's called biased versus unbiased estimators. So this is an unbiased estimator of this. So, and one thing I want to make sure you understand is, if this data was a sample, I don't know what the population standard deviation would be. All I know is my sample, right? So why does the calculator give me both? Because the calculator doesn't know. Is it a sample or a population that you put in? The calculator doesn't know, so it just gives me both. So if it was a sample that I put in, this is accounting for the fact that it's just a sample. It's trying to correct it so it's closer to the real standard deviation. What's funny is, what you're thinking about is, some samples will be actually too small, some will be too big, but overall, if I do the adjustments, they'll average each other out, and it will become exactly the standard deviation of everybody.
So how do they come by the adjustment?
Here we go. You ready? All right. We're actually not. I'm not going to entirely answer that question because it's a little bit beyond the level of math required for this course. But I at least wanted to make sense why it might be something like this. You ready? So let me remind us. The formula for population standard deviation, let me put it up here. And this is what I warned you guys about. The big thing with statistics is all the Greek letters and knowing when to use which formula and when they tweak a little bit, when they adjust a little bit. That's what gets people down. Okay. So here's the population. Would look like this. Let me just say the population variance so I don't have to draw a big old square root. And here's the adjustment for a sample. Of course, I put the sample mean symbol there, right? Here's the adjustment. You ready? Here's the big old adjustment. There. That's it. So it's not too far above the math most of you guys have had, but it is a little out of our reach. to see why that's necessarily the thing that works. But let me explain a little bit about n minus 1, because it's very, very important, this n minus 1. And real quick, just make sure you guys understand. Remember, does this make sense? If I take a sample, those values will be closer to their own mean than whatever the real mean is. Does that by itself make sense? Let that make sense. Which means, if I didn't adjust for that fact, every standard deviation of a sample, almost every standard sample would have too small of a standard deviation. Does that make sense? If they are closer to their own mean, then when I do a standard deviation for them, that's the distance away from the mean. It's going to be smaller than it's supposed to be. All right, I think I got some of you guys are at least humoring me. Go on. All right, sorry. I really want this to make. Do you really have to understand what I'm saying? Not really. Just plug and chug shit and go. But I really hope you guys kind of get a feel for why this is. So how do I make a division problem? If it's going to be too small, how do I make it become a little bit bigger? I divide by a little bit less. So does it at least make sense? Any adjustment I make, I want to make it a little bigger. Because most samples will will underestimate the real standard deviation. So I make them all a little bit bigger by dividing by one less. Doesn't that make it a bigger number? If I divide by less, the answer becomes bigger. Yes?
So what you're saying, the population is already, the number is big, but to make the sample bigger, you're doing n minus 1.
Yes, so this is an adjustment because it's only a sample.
Okay, gotcha.
Why is it exactly n minus 1? We can't totally get into that. I'm sorry. There's going to be certain things in here that depend on at least calculus, if not further. And this is one that depends on a mixture of things. Now, real quick about n minus 1. Let me see if you guys are cool with this. This is sort of related to what we talked about earlier. If I told you I had 4 numbers that average to be 10, can anybody tell me anything about the numbers? I got 4 numbers that average to be 10. There is one thing you can tell me. They have to add up to be 40. Is that cool? Because 40 divided by 4 would be 10. Whatever they are, they have to add up to be 40. So let me say something weird. How many of them can I just not even think about the 9? 8, 7, 28, 40. Can I just make up numbers for all 4 of them? What's the most I can just make up shit for? Why 3? So for example, so I have 4 numbers, and I know the average is 10. Could one of the numbers be 18 billion?
Yes.
Of course. As long as another one is like negative 18 billion or something, it brings it back down. Does that make sense? So I can't make up all 4. If I just make up all 4 of them, then the average could be who knows what. So what's the most? What's the most freedom? What's the most freedom that I have to make up numbers? I can say that's 3, that's 11, that's 17, and now I gotta get serious. Now I go, oh shit, it's supposed to add up to be what? 40. What do I have so far? 31. So the last number has to be 9. So how many degrees of freedom do I have? 3. So what was n? What's n?
4.
So what was the degrees of freedom? 1 less than that. Oh, n minus frickin' 1. So the n minus 1 actually comes in to statistics. Statistics? All right, an easier way to say statistics, by the way, is statistics. Some students agree with that a little too much. The n minus 1 comes into play a lot. If you've taken any stats before, you know that. You know it comes up later. And entire distributions are dependent upon n minus 1. Anyway, so that's just to show you n minus 1 has its own importance. Does that explain why it ends up here? Not really, but oh well. I can't do that. Sorry. Okay, how are we doing so far? Okay, so let me give you this handout, and I'm going to give you a list of data that I want you to calculate standard deviation for, and then it should be just about time to go. I mean, statistics, I might be the only one in the room, but I love reading about the history of statistics. It's crazy. Statistics is humans saying, oh look, there's math. Let's make math do some shit for us. And like we just made math tell us how spread out the data is. I'm not even counting here to see what happens. I don't know if you understand what I'm saying. That's why I love stats. We just create a formula that does what I want it to do it. And then we see how useful it is after we've made it. Right? So we're going to see what standard deviation does for us throughout the semester. We just created it. We didn't work to it. So I'm going to put up here some data. And do you see how I try to do this to label the column headings with what you would put into the calculator? Do you see that? L2 is L1 minus, in this case, 5. Where did 5 come from in that example? It's the mean. So whatever your mean is, it's not always 5, it's not always 3. It's whatever the mean is. So let's say I'm going to put these in order. They don't have to be, but just to make it easier to look at. These are grades on a 10-point test. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16. That's pretty good. I like that. Let's see. So I want you to try to do like we just did. And you can do it in the calculator if you want to. Create the table and figure out the standard deviation for this. Whatever you mean is rounded to, we'll make it 2 decimal places. Is that cool? If it needs to be. I don't even know. Hopefully it comes out to be 6 or something. That'd be nice. So if you have a calculator, let's just do this here. Yes, sir.
I have a question. The sample. So like, it says L1 minus 5. Where do you get 5 from?
Yeah, where'd 5 come from?
The mean.
Right above that, part A, the mean. Because what's that column supposed to be? It's got to be x minus the mean. Oh, let me see it. This is a sample here, right? I have to be very specific. Real quick, if the problem does not say, you assume it's a sample. Because what we normally work with in statistics, a sample. If I have a whole population, I'm going to freaking scream it from the roof. I got a population! Because normally in statistics we don't. So when we have a population, we're like, oh, thank God. Everything's easy. I don't have to guess about shit. So if it doesn't say, you have to assume it's a sample. And why is that important? Because the formula is a little bit different, right? So this is a sample. Use the same formula as on this handout, the n-1 adjustment.